Hello again, everybody. Now, remember yesterday in lecture number 1, we started a process of self-assembly, and that's the self-assembly of everything in the natural world, and that includes you and me. Now, we started with the standard model. That's just the bits we need to make an atom, something that's stable. There are hundreds and hundreds and hundreds of particles in the universe. We see them in the laboratory, but they're not stable. They don't exist for a long enough period of time to do anything. But from the standard model, we built stable particles, one the proton and the electron, and also the neutron, which is only stable if it's inside an atom, if it's bound to the proton. So if you want to go through that one again, then it'll get you back to where we want to start today, which is we've got matter, and from that we're going to start the process of self-assembly of everything we know in the natural world. Now, matter, as we saw in lecture number 1, really isn't what we can imagine. We see so many pictures of it like this with little balls, but it's not like that. There are no little balls. We saw that we're just quantum entities, which can sometimes be a wave and sometimes be like a little particle in space. I can show you that with these two remarkable photographs. If I look at this is the path taken by an electron. It looks like a little thing in a little space, but if I show you this photograph is not made with light. The wavelength of light is too big. This photograph is made with matter, because matter has a wavelength. This was made by an electron microscope, but you could make a photograph with a microscope using neutrons or some other kind of matter, because it really is two different things at the same time. And it can also be in two places at the same time. Now that's counterintuitive to us. We don't see things in two places at the same time. But because of the way the human mind works, if you did see things in two places at the same time, it would be normal. Now it's quite normal for you to look through solid objects every day, and you don't question it because you grow up with it. Now that's going to be very important when we look at human behaviour later. Now, there was one feature of matter which is very important. It's a recurring theme. Matter is not like this. This is fantasy. There are no little balls. There's no thing there. A thing is always a product of the quantum entities. So, if we think of matter, something with a nucleus like this, and an electron like this, a kilometre away, it's a cloud of empty space, an awful lot of empty space, a square kilometre of empty space. And that means if everything's made of empty space, it's all right to look through solid objects because there is no thing there. There is an interaction with light when I look at the table, but that's something very different. Light goes into things, the light comes out of things, there's something I can see, but really the matter here, I see absolutely nothing. So, if this is what matter is really like, empty space, and then to the electron, empty space, everything it makes is empty space. So, the Earth is all really made of empty space. And if particles don't interact with the forces I need to make that, they just go straight through the Earth as if it is not there. Now that raises an intriguing possibility that if there's another universe which is not made from the standard model, but other particles which simply don't interact with this, there could be another universe here, now, living right inside us, or us inside it. It's a very real possibility, because there really is no thing there. So here's my empty space. I'm going to see that theme again when I look at this thing. Now it's 4 light years to the next star from the sun. That's an awful lot of empty space. So this is all empty space with a few little tiny areas where something else is happening. Matter is really very much like that, but we're looking on a very different scale. And if we look on the biggest scale that we know, now this is a cluster of galaxies very, very close together, but in most of the universe they're spread out. Once again, there's lots and lots of empty space and a few small areas where the matter can exist. So we've put matter into existence, and from that we need to start the process of self-assembly using the parts from the standard model. So we're going to use the quantum world to build the classical world, the world which you and I live in. Now, the quantum world has very, very different laws from the classical world. And when we started to find the laws, here's Isaac Newton, who was really the first person who started to put everything into mathematics. Now, he doesn't make the laws, he finds them. We find them. They're not our laws. Why should they be? It's not our universe. So if I want to look at how something moves in a classical sense, I use an equation like this. But if I want to see how a quantum entity moves, I have to use an equation like this. This is very, very different, and it does allow for that to be in 2 places at the same time. So how can this be? How can we have 2 different sets of rules, and all these, you can't get them from this. You can't get the second from the first. Doesn't seem to make sense. Well, I'm going to demonstrate that. And this is a very difficult problem. In physics, it's called the measurement problem. At what point does the quantum world change into the classical world? Well, as yet we don't know. But we find that even molecules have quantum behavior, very, very different. Now I can demonstrate that using my plasma ball here. So we need to switch the lights out so we can see what's happening. Now, in the classical world of tables and things and you and me, it's all very predictable. It interacts with gravity. If I throw something, I know exactly how it will move and where it will land. But look at this, inside here, and this is like a quantum entity. It's all very, very different. There's my little region of space in which something very different is happening from the matter which is making the table, which is a net result of what's happening inside here. Now, if I try to predict where any of that energy is at any one time and any of the particles, I can't do it. It's impossible. But here, in the glass, I can make a prediction. If I throw this, if I throw it out of the window, I can predict exactly where it will land. Now, that seems to have too much uncertainty for me. I don't really like it, because the human brain wants to have everything like this in terms that humans can understand at an everyday level. But why should it be like that? It's not our universe. Now, I can change this and make it into a set of certain probabilities by touching it there. Now you can see as the electrons are moving from here to here, there's a lot of uncertainty, but they always arrive exactly in the same place where I put my finger, so I've changed something, and there's a point here where it changes. Now the micro and macro world is very much the same thing, we just don't know where that point is. So that would be the measurement problem in physics. Where is that point? Well, I'm sure we'll find an answer to that, and that would mean we could put these two together. So what I'm going to do in the process of self-assembly is to show how all the quantum entities have consequences which allow the self-assembly of all the natural world to take place. So let's start with the solar system. Now, we imagined in lecture 1 just being hydrogen and nothing else. And hydrogen interacts with forces. We need some gravity to make anything out of space start to interact. And we need electromagnetism to make all the small things. I also need a very strong force to make elements. If I'm going to try and push two protons together, which are positive, they're going to repel. So I need something stronger to bind them together. But there's a problem with that. If there's a stronger force, why doesn't that bind everything together? Well, it only acts over a tiny, tiny distance, so it can't reach out and grab anything else. You see how it all works? It's very clever, and we couldn't possibly have thought of it by ourselves 300 years ago without observing things which are really very counterintuitive, but that's how it is. Now, let's start with the solar system. I need to make a solar system just using hydrogen, and that means I've got no elements, there's no stars, no bits of rubble lying around, nothing, just hydrogen. Now, we looked at this in lecture 1, the visible forces, the forces that we could relate to because we see them all the time. Gravity and electromagnetism. We call it electromagnetism because it's really one force with two faces. It's like looking at a coin. I can look at this side or I can look at this side, but I can't look at them both at the same time. I teach it to the children using a Mobius strip. If you look at my thumb, you'll see just by moving this, I can cover both of them at the same time, electromagnetism, and I don't have to take my thumb off the paper to do it. So electromagnetism really is very, very important because it also has poles. It's very, very strong. 10 and 40 zeros stronger than gravity. Now, if it didn't have poles, it would be so strong it would collapse everything and make it all disappear. That's a theme that you'll see again and again. In fact, even if we get enough gravity somewhere, it collapses matter itself and makes it all disappear. So this is a force which is using these to balance or cancel itself out. And if I get a tiny bit of asymmetry left where they're not balanced, that can also be one of the forces of self-assembly. So we're going to have to make the solar system using, well, we're going to start with gravity. All things have gravity, but because gravity is so small, 10 and 40 zeros smaller than this, it's very, very weak. But out in space, that doesn't really matter because there's no resistance to things moving. Well, there is a small resistance, but I need to have a lot of atoms before I can start to see the effects of gravity, an awful lot of atoms. But that is going to make patterns which are going to tell me what is happening. Patterns which have symmetry and asymmetry. size and ratio, shape, periodicity and self-similarity. Those are the patterns which, when I look at the solar system, I start to see what's happening. Now, when you teach children about the solar system, if you don't teach them to look for the patterns, you're not teaching science. You're just telling them names. Well, that's not science, it's just nonsense. If I look at this, I start to see some patterns. Number one, they're all spheres, because gravity doesn't have poles. It also makes big spheres, because it's very weak. It doesn't collapse the sphere. There isn't too much gravity. But I also see 4 big ones here, which all have rings, and they all have a lot of moons. 4 small ones here. And what this doesn't show you is that these are very close to the sun. And these don't have lots of moons, and they don't have rings. Well, that pattern is telling me really what's happening and how it's self-assembled. Now, we're going to remember the spheres. Spheres are made by gravity. It can make other things. But because gravity is so small, if the thing is not big enough, it can't pull itself into a sphere. Now, this is an asteroid, and here you can see it has a tiny little moon. And you might be asking yourself, if they're being pulled together by gravity, why doesn't the moon just fall into the asteroid? Well, that's the question of why doesn't the whole solar system fall into the sun? Well, we need to answer that question a bit later. Now, remember, we don't have any elements. Everything I can see around me here is elements, and those elements we find in the earth. Well, if I'm starting with no elements, it's impossible that these elements can have just, we made them, or something like that. They've got to come from somewhere. Well, stars make elements. They self-assemble. So let's start our process of self-assembly. Now, when you pull something together with gravity, there's going to be bits which have more gravity and bits that have less gravity. Some bits are going to be winners. Now, when I look at a shape like this, I see that this is the winner, and this needs to be the winner for the rest of the solar system to exist. This is an awful lot of matter. Here's the Earth. Now, just imagine how much you weigh on the Earth, and I weigh 76 kilograms on the Earth because I'm interacting with the gravity from the Earth. But if I could stand on a bubble with this much gravity, well, I simply couldn't exist, and nor could anything else. So it's very important that the ratio of gravity and electromagnetism isn't too small a ratio, so that the gravity would always overcome the electromagnetism and not allow chemistry to take place. We're going to see why that's important later. Well, there's no chemistry taking place here. That needs to be on much smaller places which don't have so much gravity. Now, let's see what this is and why so much energy is coming out of here, and how that can happen for such a long time to produce stability. We need stability for you and me to exist. That stability, equilibrium, is needed for the amount of time for evolution to take place. And this is deep time. We're talking billions and billions of years. That's another lecture. Let's go back to assembling the sun. I've got to have an equilibrium. The sun must have most of the matter to keep the rest of the solar system in order, if you like. So, if we look at the sun here, the sun has 99% of all the matter in the solar system. So it's controlling the solar system. 99% of all the matter. The rest of it is 1%. Now, what stops the solar system all falling into this? Well, you all know that things orbit, but why do they orbit? Why don't they just fall in? Well, we need something from the Standard Model to explain that. We need the Higgs field. Now, here's something travelling in a straight line through empty space. There's no acceleration, there's no change. If things didn't have mass, then everything would whiz around maybe at the speed of light. But it doesn't do that. If I push an object in space, there's a relationship between the mass and how fast it moves. And that relationship is to do with an interaction with the Higgs field. So I'm going to fill space with the Higgs field. Now, because we've now found the particle that it's interacting with, the boson, the carrier of that, we know that our Standard Model is something that we can trust. Now, if I pull something like this, I've got to accelerate it in this direction. And I've got to accelerate it through the Higgs field. There's going to be a resistance. Now, you can see that as the matter starts to spiral down towards the sun, if it spins, I start to get a shape like this in a disk. Now, I've seen this shape before in a galaxy. So that tells me that the laws of physics are the same at this level and at this level. I've got something in the middle which is pulling. Here I've got a very low air pressure, and here I've got a black hole. That's an awful lot of gravity, but it's making the same shape. Now, the early solar system would have looked very much like this. Well, that doesn't look like planets to me, so something else must be happening. Now, I've drawn here a representation of the solar system. Atoms are always drawn wrongly in books because you can't draw them. I can't draw my electron a kilometre away over here. The solar system is the same. I can't draw it to scale because it's too big and there's too much empty space. So here's 99% of the gravity. Close in towards the sun, there's 4 spheres, which are all made of heavy elements. The Earth has iron, lots and lots of iron. Well, that's not a coincidence, because they're all terrestrial. That means they're all made of those heavy elements, silicates, rocks, basically, and water, which is heavy. And that's all pulled right in here. Now, you know, if you watch some water going down the sink, as it moves in here, as it gets closer to the middle, it starts to spin faster and faster and faster. I have to increase the acceleration of the turn, and there will be a point at which that acceleration, that being pulled through the Higgs field, is exactly going to balance the pull of gravity here. So it puts some order into the solar system. So when the Earth orbits here, it stops just in one place with the pull of gravity balanced by having to accelerate it through the Higgs field. And when they balance, the Earth stops just here. And because the Earth has a size and a mass, it can only stop here. It can't stop anywhere else. Now that's going to put all my heavy elements down here and close towards the sun. Now, the other 4 planets, which are not made of heavier elements, they're all gas. They're all a long way away, and they're a long way away from anything else. But if I look at the numbers, I start to see a pattern. Now, if I say the Earth is 10 units from the sun, I've got here Mercury at 4 units, Venus at 7, the Earth at 10, Mars at 15. But Jupiter is at 50. Saturn, 100. Uranus, 200. And Neptune, 300. Now it must be like that, because if everything has gravity, if two things get too close together, they start to orbit each other. So this system here has to be controlled by this. If there's something too close to this, it can become part of this system. And what we find is that I see that pattern in other places in the solar system. I see some similarity, and that I see here. Saturn. I see a disk has formed and patterns in that disk, which we're going to look at later. But the solar system really, a long time ago, would have looked something like this, and then it has to order itself, and it just keeps changing and changing and changing until it finds equilibrium. And the process of orbits being pulled through the Higgs field is what balances the gravity. It gives me equilibrium. It gives me orbits. It's not the whole story. There's some rubble in the solar system here. This is where the asteroids are. This is where there's still some chaos, some disorder. There's too many bits. Now, this, you can see, is trapped between this system and this system. This pulling this way and this pulling this way, so it can't find any order. It can't find an equilibrium. It can't make itself into another planet. Now, we've got something here, the Higgs field, the need to be pulled through something and the resistance to that. If there's no mass, there's no resistance to it, everything will just spiral into the sun. It doesn't do that. I've got some balance, some equilibrium. But there's also precision. I need absolute precision for this solar system to have enough stability. Now, your watch counts the movements of the solar system. Now, the solar system is much more accurate than my clock. Much more accurate. How can that possibly be? It's such a big thing. How can it be just controlled by gravity and being pulled through the Higgs field? Well, there's something else which is controlling the solar system to give precision, and that is resonance. Now, we're all familiar with resonance. When you listen to music, some notes sound very good together and some sound very bad together. If they sound bad together in the solar system, they keep changing until they do fit. Let's show you how it works. Now, Jupiter is a very good example because it has 3 moons which have orbital resonance with each other. Now remember, as you get closer to something, you must travel in the same distance in the same time. So if this one is 1, this is 2, and that's 4. If this goes around the planet 1 time, this will go around just half here, and this one just a quarter here. Now let's show you how this works, because it's very important. So imagine this goes around the planet once. It's close into the sun. It must be going really fast, otherwise it's going to go into the planet. I can show you this one. It's a moon called Io. If you look at this picture here, there it is, really close to Jupiter. Too close for its own good, because the forces inside Jupiter are trying to rip this moon to pieces all the time, and that creates inside it heat, and that heat means that this has more volcanoes than anywhere else in the solar system. Well, that's another source of energy in the solar system besides the sun, which is going to be important when we look at life later. But look how close it is to this giant planet. It can only just exist here if it's spinning around really fast to stop it disappearing into the planet. So there's my moon. Io, Europa, and Ganymede. So let's see what happens when Io goes around once. Europa is going to end up here. And you can see they're going to pull each other this way. And Ganymede is going to end up just a quarter of the way around here, which is going to, they're all going to pull each other. But I've got balance and I've got precision. If Io goes around 2 times, then this is back here, and this one is now over here. This one's gone back to the starting place. And again, I can see it all balances. I've got something which is cancelling itself out with absolute precision. Because if it's not precise, it just keeps changing until it is precise. If this goes around 1, 2, 3 times, this one, and 1, 2, 3, it's back here. But this one is now here. So everything pulls and balances once again. And that's orbital resonance. And we can see that resonance here. If we look at Saturn's rings. And that's very, very complicated because Saturn doesn't just have 4 moons, it has 60 moons. And they're all producing a gravitational effect on all these pieces of ice here. Now, if they didn't do that, it wouldn't be shiny because this is really made of millions and billions of pieces of ice. Now, I do get black lines here where there's simply all that resonance adds up and cancels itself out to a net effect of 0 here. So nothing can exist here, but here it adds up. So I get more of it here. Now, I'm just going to ask Sophie to come in and look at this because this shows the complexity which I get from a gravitational field, a Higgs field, and orbital resonance. I get this beautiful pattern which is all the rings together. And this is what the early solar system would have looked like. Just a seemingly, it looks like chaos to us. But it's not chaos, it's precision. Now I can show you that precision if I look at this little black bit there. That is an exact number where nothing can exist. It's just simply the total representation of the gravitational fields of those 60 moons and of Saturn as well. Now when you look at something like this, the human brain can actually turn something like this into a meaningful pattern if we know how to do it. Now you do that intuitively when you listen to an orchestra on speakers. A speaker produces a single complex wave of music, just one very, very complex wave of music that would look like this if you represented it. But your brain, because it needs to understand the patterns needed to understand speech, will separate out all that and turn it into the music. That happens inside your brain. Your brain knows that this resonance here is a trumpet, or over here is somebody's voice singing. And it must be able to understand that, otherwise you couldn't understand spoken language. Now, we've built ourselves a solar system, but there was a problem. The Earth has elements. Well, they can't have come from our sun because they're all in there. There must have been another star before the sun which made the elements which now make up the Earth, which we dig out of the Earth. So let's tell that story. Now that star was much, much bigger. That means even more gravity than our own sun. So how can so much gravity not just disappear in on itself? I need to have some equilibrium. I need to have a balance, if you like. Now, there's also an awful lot of energy coming out of the sun, and it comes out for a long time. That must be coming from somewhere. Now remember, I'm only allowed to use parts of the standard model, the forces and the parts that we used and the force carriers. And energy. Energy and matter are equal. They're the same thing. I can change matter into energy. And that's exactly what stars do. And they have to do it by using gravity. I can only use these parts from the standard model to make everything. Now remember my ratio, 10 and 40 zeros. That is a huge number, a number you can't even possibly imagine. But that ratio tells you the size of the sun, gives you a clue as to how much matter you need to push two protons together using gravity. So, if I could count all the particles that make the sun, there's the Earth, that would be a number that I can't imagine. And I need that number of particles to push two repelling particles together using this force. Now, I can demonstrate this ratio to you just by using this. All the particles that make the Earth, the whole Earth, all the mountains and the oceans and all the hot iron inside are pulling this magnet down. But because there's a repulsive force between the magnets, it's much stronger than the whole Earth. That little magnet has a much, much stronger force than the whole Earth. And remember, this matter is made of something that cancels out most of that force. There's just a little bit of imbalance doing that. If that was pulled down to this, but this was all plus and this was all minus, well, it would all just disappear. That matter couldn't simply exist. So it's very clever, really, but it has to be like that. If I want things to happen, small things, if I want anything small to exist, I need a strong force. But it must cancel itself out. If I want to make big things, I need a weak force. And the ratio between them is the driving force of creation, of how things self-assemble. Let's go back and see what's happening in the sun. Now, here's the sun. Just think of no energy coming out, but there's an awful lot of gravity. 300,000 times more gravity than is on the Earth. It's just because I've got lots of matter together. That starts to squeeze the matter which is in the middle. Now the particles which are in the middle, I'm going to have deuterium, which is one plus and one neutral particle, and we showed in the last lecture how I can make this using the same bits from the standard model. And here I've got some tritium. Again, just one plus, this is hydrogen again, but it's got two neutrons. Now, if I want to push those two pluses together, I've got to overcome this 10 to the 40 zeros. That's why I need so many particles. That's why I need stars to be so big. But if I push these together, the strong force, which remember only acts over a very short distance, will grab these two and send one of these away. When it grabs those two and sends one away, if you like, I've got 1, 2, 3, 4 bits of binding energy there. Some of that is going to be released, and I'm going to make a helium nucleus. Now that energy which is coming out, the energy release rate, inside the sun, it's a very slow process. We see it on the Earth when we set off nuclear explosions. So the sun is like using gravity to hold together a nuclear bomb. Now it only works because the energy release rate in the middle of the sun is very slow. And in fact, kilogram for kilogram, you produce 4 times more energy than the sun. But because the sun is so big, that's a lot of energy. But it's that energy that we are going to use to create an equilibrium, to hold the sun up against its own gravity. So here, I've got this process taking place. Protons being pushed together, releasing energy which starts to push out. And the gravity which is pushing in. Now, the size of the sun will always be a point where those two balance out. Just like an orbit is where I balance being dragged through the Higgs field against the gravity pulling me in. It stops just in one place. So imagine now I've got energy pushing out and gravity pulling in. It creates an equilibrium. And that equilibrium can last for a long, long time in a small star like the sun, because it's not too big. The star from which the sun and the earth came was too big. It burns itself out very quickly, so I don't get enough stability and time needed for evolution to take place. But you can see there's a problem here. If I keep pushing protons together, there comes a point in the middle where the atoms are getting bigger and bigger and bigger. It becomes harder and harder to get another proton into that bunch. And there's a point where I get here to make this element here, iron. Now iron is the last element you can make that if you put another proton in here, you get some energy out. So now you can see the problem. When the sun, in the middle, starts to make iron, the game is over. That's it. It's going to commit suicide by making iron. Because, remember, my balance, the energy pushing out, the gravity pulling in, well, it's like this equilibrium I've got here. I've got the electromagnetic force between the molecules of the balloon pulling in, and I've got the pressure from the electromagnetic force in the gas inside pushing out. And this is exactly what happens in the sun. I've got this equilibrium here, the energy pushing out, the gravity pulling in. Well, after you've made iron, you don't have to count very long before I switch off the energy pushing out. So the sun just goes bang. Now, that bang is very important because there's an enormous release of energy as all this matter comes down and splatters together in the middle. And that release of energy is the energy which I can use to make all the elements which are bigger than iron. So I continue my self-assembly. Now we need some of those bigger elements to make our bodies. So it's very important that it does happen. And it's also important that we put them in just the right place in the solar system, here. If I put them here or in another place, things don't work. It's very, very complex. If I look at the rings of Saturn, I see that complexity. Now, because I'm going to make living things using chemistry, chemistry is adding another dimension of complexity into the system. Now, if I look at this place here, Venus, it's very, very similar to the Earth. It's just a bit closer to the Sun. But because the chemistry was different, it's a completely different place. I don't get similarity in any respect looking at the atmosphere. The surface temperature here is 400 degrees just because the chemistry of the atmosphere is very slightly different, and that's CO2 that's causing that. Well, you can also think of that in terms of the Earth. The Earth was the same at the beginning. They're just created by natural forces, but the Earth had life. and life locks away CO2 into the earth. It takes it out of the atmosphere. So life is really creating the conditions needed for more intelligent forms of life, which need oxygen to fuel a brain which has to move very quickly. So as the earth starts to create its own conditions and change the atmosphere, the temperature is very, very different from here. I can have water existing as ice, water vapor, and liquid water all at the same time. Now, that's the story for the next lecture, where we see how, because the earth has ended up in the right place with the right ingredients, I can continue my self-assembly from atoms into molecules, and from molecules into life. Well, I hope you enjoyed the second part of the lecture. We'll see you next time.